This is the lab manual for RTD CSTR, and these are the readings that you will get. You need to calculate it for two flow rates. This is for 10 LPH and this is for 20 LPH, and you have to solve it procedure. And now we are on the precautions part.
So what are the precautions and maintenance instructions? First, you always need to use distilled water for good quality chemicals and standard solutions for titrations. Always use distilled water, standard solutions for titration and good quality chemicals. That is the first thing if you want to get better results. Second precaution is, while you are filling water in the feed tank, make sure to close all the drain pipes. It shouldn't happen like you are filling the feed tank while the drain valves are also open. So you are not able to fill the feed tank. You know what is the feed tank, right? This is the feed tank.
So once you have started filling the feed tank,
You should keep all the drain valves closed so that the feed tank will get filled easily. Second, you should not unnecessarily disturb or stop the experiment in between. If it is given that readings, samples should be taken after every minute, so you need to keep the flow of the experiment going on. You can't skip any one reading because then the concentration and the curves will differ and that will result in bad readings. Second is all the chemicals, like we have put 10 ml HCl and here and here, it should be handled very properly because these are concentrated HCl. So use proper droppers and collect them from tank properly. See, here is the dropper. So if you want to take out HCl, you need to take a measuring cylinder first. I don't have it right here. Take the measuring cylinder, take dropper, and then only using a dropper, put the HCl in the measuring cylinder. This is how you pour HCl and handle it carefully. Chemical handling is a very important thing, and you should handle your chemicals very well.
RTD in CSTR is like every molecule is either early, late, or lost in dead zones.
Whatever. To conclude this experiment, we have found the residence time E and F values. Residence time distributions has been studied. We have plotted the C versus T curve, E versus T curve, and F versus T curve.
So it's time for the discussion now. Let's dive into it.
So let us start by getting to know the technical theory behind CSTR and residence time distribution. Kaushik, can you just walk through what we did today?
Yeah, sure. A CSTR or a continuous third tank reactor is a type of reactor where the contents are continuously stirred and continuously fed with reactants while product exit at the same rate. The goal is to maintain the constant volume within the reactor, creating an environment where mixing is through a reaction or a stable.
Right, and isn't the RTD an important indicator of how well that mixing is actually happening, Kaushik?
Exactly. The RTD represents the time distribution of the material within the reactor. Ideally, in a perfect CSTR, every part of the fluid has an equal probability of exit at any given moment.
To measure the RTD, we introduce a tracer, which is an inert substance that won't interfere with the reaction. By tracking the tracer exit concentration over time, we can create an RTD PA curve. This curve gives us insight into the actual mixing efficiency with the reactor.
Precisely, the shape of the RTD curve helps us to understand how close our reactor behavior is to the ideal CSTR model. A symmetrical bell-shaped curve suggests ideal mixing, while deviation indicates the inefficiency.
Yash, you told us about the apparatus.
Right.
So what do you think why apparatus is needed for the experiments?
So-
Why is it so important?
Yeah. So the core component is the CSTR itself, which is equipped with a continuous steering mechanism, or we can say the agitator.
Agitator.
Sorry.
You got it.
Yeah. So agitator is a continuous steering mechanism to maintain the uniform mixing. Then we have a pump system, like we showed you before, that ensures a steady flow of reactant entering and exiting the reactor. Maintaining a constant flow rate is efficient because of because of the fluctuation that happens in the CSTR itself. So this is how it happens.
And the tracer, the salt solution you mentioned earlier, how does it actually help us study the RTD?
Yeah, that's a good debate. The tracer acts as a marker with the fluid inside it. The inert, it doesn't react with anything in the reactor. We inject it as a pulse. The tracer we inject as a pulse. The tracer includes the glacial acetic acid. We inject the pulse at the reactor's inlet and then monitor its concentration over the time. This concentration data let us calculate the RTD as it reflects on how long distance part of the fluid spends inside the reactor.
To add to that, the sensor used to monitor the tracer concentration are crucial. They capture real-time data on the tracer presence at the outlet, allowing us to map its progress through a reactor. This data is what we use to construct the RTD curve.
Okay, so apparatus essentially lets us observe and quantify the mixing quality. Alright, let's go over the experimental procedure.
Alright.
So how did you carry out the experiment?
So the first step is calibrating. This ensures that the reactor is at steady state, meaning the volume inside the reactor remains constant and the extra fluid flows out from the outlet pipe. Once we have achieved that, we introduce the tracer as a single pulse into it. And we further do the titration using the burette, using 0.1 normal NaOH. Moving on to Kaushik.
By pulse, we mean a brief injection of tracer rather than a continuous stream, correct?
Yeah, that's exactly correct. A pulse injection gives us a distinct signal that can be traced when the fluid flows from the outlet pipe. This concentration data collected from titration and all the experiment we did with the 14 other experiment setup, it's collected over the time, and we draw the RTD curve for the same. The shape of this curve reflects the mixing efficiency of that.
So the timing and rate of the pulse injection are critical, right? Too long for an injection period might distort the RTD curve.
Yeah, that's correct actually. The main aim for a quick concentrated pulse is to get the curve and get it in mixing efficiency. We can say that the tracer exit concentration at set interval. With the data, we can plot the RTD curve and compare it to the ideal CSTR model.
Can you tell us what can we expect to see in an RTD curve and what can be interpreted out of it?
Sure. In an ideal CSTR, the RTD curve should be resemble a symmetrical bell shape centered around the mean residence time. This indicates that all parts of the fluid are spending roughly the same amount of time in the reactor, showing how uniform mixing it is. However, deviation from the shape can reveal inefficiency.
And what kind of inefficiencies might show?
Good question. If the curve skews to one side, it could suggest channeling where parts of the fluid are bypassing the mixing zone and the exiting too quickly. If the curve has multiple peaks or an irregular shape, it might indicate the dead zones.
I think adding to that, we can also talk about the variance from the RTD curve, right? The more is the variance, the more is the distribution of the residence time, suggesting less uniform mixing. Ideally, we want a lower variance, which means lower spread of the curve, right? And lower spread of the curve and symmetry of the RTD curve.
Yeah, and variance directly imparts the quality of the final product in industrial applications.
Right.
For example, if you are manufacturing chemicals, inconsistencies in mixing can lead to variation in the product's properties.
Yes, true.
That's right. By analyzing the RTD curve, we get qualifiable insights into the reactor mixing quality. This information is crucial for industries that rely on precise control of reaction conditions to produce consistent.
To sum up, what do you think is the critical takeaway from today's experiment?
From a theoretical perspective, understanding RTD is a key for reactor performance. An ideal RTD curve indicates the efficient mixing, which is essential for predictable reaction rates and consistent
Consistent output.
output. Yeah.
Adding to Kaushik, I would also say that tracer also plays an important role in RTD. RTD, like we can say the inefficiency or how efficient it is by adding a tracer to it. And other point is also the curve, the symmetry of the curve, how wider it is, and how we can say about the symmetry. From symmetry, we can say how efficient the RTD is performing.
We can identify the dead zones.
Correct. That's correct.
Yeah, and on industrial level, these experiments insights can be invaluable. Efficient reactors with well-defined RTDs are crucial for industries like pharmaceuticals, where mixing consistency affect product quality.
Correct. Yes.
And by understanding and optimizing the RTD, companies can enhance efficiency and reduce waste.
That's true.
Thank you, everyone. I think we had a thorough discussion on this experiment.
Yeah, we should conclude.
I hope you understood it well, what our experiment aimed at.
Thank you.
Thank you.